So our homework that we had this weekend was question number 5 on worksheet number 12. We're going to take a look at that now. It says, how does the radius of curvature of an electron compare to the radius of curvature of an alpha particle? A little bit of a typo here. What we really should have said is the radius of curvature of an electron's path compared to the radius of curvature of an alpha particle's path. We don't actually care what the radius of the electron is. We care what the radius of its path is. We know that when a charged particle moves through a magnetic field perpendicular to that field, it will move in a circle. There will be a radius associated with that circle. We want to compare the two radii that we have here. Of an electron going through a magnetic field and an alpha particle going through the magnetic field. Whenever we have the word compare or something that means the word compare in a question, what are we going to do? One word. What is it? Divide. Whenever we see compare, ratio, did you say? Yeah, ratio. Okay, whenever we see compare, ratio, anything like that, we're going to divide. Now, what are we going to divide? Well, the example that I gave you guys on Friday before you left was age. I think we said, who was my example? Was it Spencer? Sorry? Let's say it was you, Spencer. Spencer, how old are you? 17? Okay, 17. And it just so happens that I'm 34. So we want to find the ratio of my age to your age. We're going to say 34 divided by 17 is equal to 2. The ratio would be 2 to 1. We want to find a ratio between two ages, or we want to compare two ages, then we're going to divide two numbers. In this case, 34 divided by 17 gives me 2. Well, in this case, I'm going to divide the radius of the electron's path by the radius of the alpha particle's path. So let's say R divided by R. Instead of age divided by age, it's R divided by R. Now, we know the radius of anything's path as it goes through a magnetic field comes from the equation Fc is equal to Fm. We say mv squared over R equals QVB. Magnetic force equals centripetal force. One of the V's cancels. R ends up being equal to mv over QB. All we're doing there is taking the R up by multiplying and the QB down by dividing. So what I'm going to do now is say RE is, well, that's mass of the electron times speed of the electron over the charge of the electron times the magnetic field strength that the electron experiences. That's all divided by, well, the same thing for the alpha particle. The mass of the alpha particle divided by the speed of the alpha particle, the charge of the alpha particle times the magnetic field strength of the alpha particle is exposed to. Now, we know that the magnetic field strength for both of them is the same, so it allows me to cross off those, to cancel it out, right? It appears on the top and the bottom, we can cancel it out. Speed is the same thing, same speed it tells me in the question. So now we've got a bit of a simplified expression here now. It says ME over QE equals M alpha over Q alpha. Now we can simplify that a little bit more. ME over QE times what? When we divide M over Q, divide it by M over Q, what's the way to simplify that a little bit? Yeah, multiply by Q over M, multiply by the reciprocal. So we're going to say Q over M. What is it you guys say in math class? Is it kiss and swap? Is that what it is? Flip and kiss. Okay, flip and kiss. Kiss and flip, whatever. Now, okay, good enough. So now we got some numbers that we can plug in here. The mass of the electron is 9.11 times 10 to the minus 31 kilograms. Divided by the charge of the electron is 1.6 times 10 to the minus 19 coulombs. We multiply that by the charge of the alpha particle, which is 3.2 times 10 to the minus 19 coulombs, divided by 6.65, the mass of the alpha particle, times 10 to the minus 27 kilograms. Now we can multiply the numerators and then divide it by, in brackets, the denominators, or we can actually simplify this a little bit more at this point. The 10 to the minus 19 can cancel. You can actually say 3.2 divided by 1.6 is 2. So we can cross off the 3.2 and the 1.6 and turn it into a 2. Basically, it becomes 9.11 times 10 to the minus 31 times 2 divided by 6.65 times 10 to the minus 27. Glad to see that Adobe Acrobat was updated successfully there. Divide those, and I think we get 1.7 times 10 to the minus 4. That sound right? Well, we got a number. What does that mean? Well, what did it mean when we said my age divided by Spencer's age is 2? Right? It was a 2-to-1 ratio. So what's the ratio here? 1.7 times 10 to the negative 4 to 1. The radius of the electron's path, of the alpha particle's path, is 1.7 times 10 to the minus 4 to 1. If we say compare, then this is how we compare. If we say find the ratio, then this is finding the ratio. Compare ratio always means divide. CRD. Compare ratio divide. I want to take a look at a few multiple choice questions right now. This one, the one we're going to start off with is question number 75. Talking about protons and solar wind, goes back to this question, this information right here. Near the end of your booklets, your multiple choice / worksheet booklets. Take a look. In about 1 minute, we'll do it as a class. 75. It says the protons in the solar wind experience a magnetic force which way? We have protons moving to the right. We have a magnetic field caused by the Earth at that point, pointing upwards towards the top of the page. What hand rule are we going to use here? We have the wire grasp rule. We have the coil rule, which you're going to have a quiz on tomorrow, by the way, the coil rule. And we have the hand rule for deflection. Which rule are we going to use? Deflection rule. The wire grasp rule is used when you want to find the magnetic field caused by a moving charge. Okay, that's not what we have here. This protons produce a magnetic field, but that's not what we're trying to find. We also have the coil rule, which obviously there's no coil involved in this. This is going to be the deflection rule where we're dealing with an external magnetic field caused by the Earth and a magnetic force. And we're going to say, since it's protons, we're going to say right hand rule for deflection. Thumb in the right thumb in the direction of the particles, which is to the right. Fingers in the direction of the magnetic field, which at that point is toward the top of the page. Palm's going to point out of the page. So my answer for question number 75 is out of the page, B. I'd like you to take a look at 76 as well. It relates to the same information, but this time you're trying to find the radius of the path of these particles as they're deflected out of the page. So have a look at this question now. It says, assume the velocity of the solar wind particles is perpendicular to the magnetic field. What are they telling me there when they say it's perpendicular? Well, the hand rule that I used already and the equations that I've learned to analyze the charged particle's path in a magnetic field are all valid. If it was parallel, the force would be 0, and we couldn't do this question. If they weren't parallel or something other than perpendicular parallel, then it's theoretically possible to do the question, but we couldn't do it because we haven't learned how to do it. Basically, they're saying that since you're looking for the radius of the path, and since they're perpendicular, you're going to do this. FC is equal to FM. That's what you're always going to try whenever you're looking for radius of a charged particle in a magnetic field. Ethan? We're going to say mv squared over r equals qvb. These cancel. Solving for r, the r goes up by multiplying, qb goes down by dividing, becomes mv over qb. Now we know the mass of the protons is 1.67 times 10 to the minus 27. We're given the speed of the protons in the question up there, 8 times 10 to the 5 meters per second. We're going to divide that by the charge of the protons, which is 1.6 times 10 to the minus 19. And then we're going to multiply that by the magnetic field strength, which was 1.1 times 10 to the minus 7 Tesla. So these things are entering the Earth's magnetic field. The magnetic field strength right up here, way up here, a certain distance away from the Earth, is weaker than the magnetic field strength down here by the Earth, right? Do you guys remember what it was on average near the surface of the Earth? 10 to the minus 5-ish? Does 10 to the minus 7 seem reasonable for way out there? Yeah, probably. Right? In the end, that's the number they give me, so that's what I got to go with here. Do the math there. And I don't remember what it worked out to be there. Does anybody have an answer for that? 9, 9.2 times 10 to the minus 10. What'd you get? 7.59? Yeah, 7.59 times 10 to the power 4 is it. If you didn't get that, try it again. Make sure that when you multiply these two numbers together and you divide by this number on the bottom, make sure you put these into brackets on the bottom. Because if you don't use brackets, then what you're going to do is effectively put everything you're multiplying it by as a numerator as opposed to a denominator. So make sure you get that number. If you can't, then let me know and I'll try to go through with you here. By the way, we expressed that ABCD 7594. I want to spend a few minutes now almost going back, talking about some stuff from our last unit, almost. Our last unit was on electricity. This unit is on magnetism. Why are we talking about electric current now as opposed to last unit? Well, last unit, if you noticed, was static electricity. We didn't talk about electric circuits or electric current. It was all static, the buildup of electric charge. We're not going to talk in detail about electric current now either, but we need to know a little bit about it so that we can solve our next type of magnetism problem. So let me define it here first. Electric current is the rate of flow of electric charge. And what do we mean by that? It's the rate of flow. It's not how fast the charges are moving. It's not how fast the electrons are traveling, but rather it's how many electrons are traveling per second. So let's say we get two people standing on the side of the highway. Jack is standing there with a radar gun. Okay, what's Jack measuring? Speed of cars as they go by, right? He measures one of them is 112 kilometers per hour, then 108 kilometers per hour, then 121 kilometers per hour, then 106 kilometers per hour. So he's measuring the speed of these cars. That's not analogous to electric charge. Megan is standing on the side of the road and she's counting the number of cars that are going by per second. So she's got her phone out, she's timing the cars as they're going by. She's counting 1, 2, 3, 4, 5. 5 cars just went by in 1 second. 1, 2, 3. 3 cars just went by in 1 second. 1, 2, 3, 4, 5, 6, 7. 7 cars just went by in 1 second. Megan is measuring more traffic, right? How many cars are going by per second. That's what electric current is. Not the speed as measured by the radar gun, but rather the traffic as measured by Megan counting how many cars are going by in 1 second. You can have cars that are going really, really fast, but not very many of them. So you can have, context of cars, a high speed, but a low current, right? Low traffic. And you can also have the opposite of that. You can have a low speed and a high current because there's lots of them going by in 1 second. They're not the same thing. They're related, but they're not the same thing. Electric current is not the number of cars, obviously, that are going by in a second, but the number of coulombs of charge that are going by in a second. It's given by the symbol I. It's a capital I. It's equal to Q over T, charge divided by time. Now, what are the units going to be? Well, if you look at charge, it's coulombs. Look at time, it's seconds. But a coulomb per second is often abbreviated as an amp or an ampere. 1 amp is 1 coulomb per second. Use whatever units you want there, coulombs per second or amps. Just be prepared to see and recognize both of those. All right, I'm going to give you what might be the second easiest question you're going to see in Physics 30. The first one, if you remember, we talked about work in electric fields. The change in electric potential energy was equal to the work, and the number that you were given in the question was simply the answer. I said that was the easiest one. This is probably the second easiest one. Calculate the current in a wire through which 20 coulombs of charge pass in 4 seconds. Well, current is I, charge is Q, time is T. So current is charge divided by time. We're going to divide these two numbers, 20 divided by 4.0 seconds, and we end up with 5.00, I should say, units. Bless you. Units would be coulombs per second, or we could say 5.00 what? Amps. You're not likely to get a question on a test that just simply asks you for current, but there is a good chance you're going to have to find current to use in another question. We'll talk about those questions in just a few minutes after you've taken a look at these two questions on page 603. Going to be ridiculously quick for you. Just go through them real quickly, and then if you need help on them, we're going to go over them as a group. Otherwise, we'll just move forward to the topic that we actually use this for. All right, if those are good, we're going to move on to our next topic here, which is what we're going to use this whole idea of electric current in, and which is what we're basing tomorrow's lab activity on as well. This whole idea of electric current going through a wire in an external magnetic field. Call it the motor effect sometimes because it's the basic principle behind the electric motor, which we'll talk in a little bit more detail about in a couple of days. Basically, the concept is this. If a charged particle moves through a magnetic field, let's say this is our magnetic field. If a charged particle, like an electron, moves through a magnetic field like this and experiences a force according to the deflection rule, thumb to the right, fingers down the page, palm points out of the page, then if that charged particle is inside a wire, it will also experience the same magnetic force. Moving through the air, it experiences a force out of the page. Moving through a wire, it experiences a force out of the page. The thing is, when you have a charged particle moving through a wire, you don't just have one of them. You got lots of them. So here's one guy that's moving through this wire, experiences a force out of the page. So does this one, and so on. All of the electrons that are moving to the right there experience a force out of the page. Now, they want it to go in circles because that's what charged particles want to do when they're in a magnetic field. But they can't go in a circle in this case because the wire prevents them from going in a circle. Right? They have to stay on the wire, and as long as they're in the wire, they can't be moving in a circle. So what is it? What happens instead? Instead of the charged particle number one, experience a force out of the page and going in a circular path like we've learned so far. Same thing with charged particle 2 and same thing with particle 3. What happens is that these charged particles all experience a force out of the page and drag the wire along with it. So it's not just the particles experiencing a force out of the page, it's the wire itself that experiences a force out of the page. Now, the force on each of the particles could absolutely be described by using the equation QVB. But the force on the wire itself, due to all of these particles moving through the magnetic field, is equal to I. What's I stand for? Current, amps. That's why we just looked at electric current so that we would learn what that was, right? It's the current strength times the length of the wire that is perpendicular and exposed to the magnetic field. So if it's not perpendicular, it doesn't count. Okay, if we have a wire that's going this way, doesn't count. The force on it would be 0. Perpendicular and exposed to the magnetic field. What do we mean by that? Well, got to be perpendicular, but we also pay attention to the length of the wire that's in the magnetic field here. This length of the wire doesn't matter. It's irrelevant. Okay, the part of the wire that's perpendicular and inside the magnetic field. That's what L is. Times the magnetic field strength. There's a little symbol we're missing over here in the first equation. What is it? Yeah, the little upside down T, perpendicular. This is dependent upon the velocity being perpendicular to the magnetic field strength. Well, so is the second one. If the charged particle needs to be moving perpendicular to the field to experience that force, then the wire with the current in it has to be perpendicular to the field to experience this force. Got it? How do you think you'd find the direction of the force on the wire? Hand rule for deflection. We're not going to learn a new hand rule here. Okay, if the force on this particle is out of the page, and the force on this one is out of the page, and the force on this one is out of the page, well, then the force on the wire that carries these 3 electrons is going to be out of the page. Just going to do the same thing as you did before, except that there's a new equation that describes it as opposed to the old one. All right? Couple sentences here, guys, just to kind of summarize what we just said. We say current carrying wire or a conductor. Sometimes we say a current carrying conductor consists of moving electrons inside a conductor. We're just telling you what it is. Hey, it's moving electrons. It just happens to be inside a wire instead of moving through the air. Now, those electrons that are moving through the wire or through the conductor, they experience a magnetic force. And they want to go in a circle, but they can't because the wire prevents them from going in a circle. But they still experience their force. But it's not just one electron experiencing the force. Now it's lots of them. Those lots of electrons, as they experience a force in a certain direction, drag the wire along with it. So not only do we get the force on the electrons inside the wire, given by the equation that we learned last week, but we also get the force on the wire itself. And we could find that direction by using the deflection rule. If it's electron current, we'd use the left-hand deflection rule. If it's conventional current, we'd use the right-hand deflection rule. Ethan? Yeah. Let's do one example and then we'll call it a day, or maybe we'll spend a couple minutes reviewing for tomorrow's quiz on the coil rule. 12.4 on 605, it says an 8.5 centimeter length of wire, conducting wire lies perpendicular to an external magnetic field of 4.20 millitesla. We got a couple units here that we got to make sure we convert. There's a negative charge flow or electron current of 2.1 amps through the conductor. What's the magnitude and the direction of the magnetic force on the wire here? The magnitude of the force on the wire would be F is equal to ILB. The magnitude of the force on an individual electron inside the wire would be QVB, but that's not what we're trying to find. We're trying to find the cumulative effect of the force on all of the electrons, or the total current moving through this wire. So we're going to say I, which is the current 2.10 amps, times the length. This length right here in the magnetic field is 0.085 meters. We don't care about this part of the wire. How come? It's not in the magnetic field. We don't care about this part of the wire. Well, there would be a magnetic field out here, right? We don't care about this though because it's not in the main part here, and it's also parallel to the magnetic field. Right? We care about the part inside here that's perpendicular to the field, 0.085 meters. The magnetic field strength is 4.2 times 10 to the minus 3 Tesla. And we do the multiplication there. What do we get? 2.1 times 0.085 times 4.2 times 10 to the minus 3. I get 7.18 times 10 to the minus 2. Anybody else get that? Should be 10 to the minus 4 here.
I did the same thing on the last question.
Yeah.
It was like milliseconds.
Okay. Good. Now what about the direction here? Well, we're talking about electron current going into the page here. So we're going to use our left-hand rule for deflection. Thumb in the direction of the particles. Which way is the field pointing here? Doesn't tell us, right? We know this though. Magnetic field goes from north to south. So thumb into the page, fingers from north to south, palm's going to point upwards toward the top of the page. Sorry, another correction here. That should be 7.50.